plane moving horizontally this way, okay? At location A. At location A, we have this physical r, we have this physical theta, and we can see that this this velocity is constant. So we can see that the components of velocity are like this, inward and that way. Now we did a lot of talking a few minutes ago, but let's look at this on the mathematics. This is pointing inward, and we know that V sub r from our governing equation is r dot, right? And you can see clearly that that's in the negative r hat direction, r hat pointing that way. So this is clearly less than 0. That should feel good. The theta-directed term is clearly this way, which happens to be at this instant in our theta hat direction of increasing theta. And that term is equal to r theta dot. And we know that r is positive, therefore that implies that theta dot is positive. So theta dot is greater than 0. Everything okay on the math? Let's look at the acceleration there. The acceleration at that same point is made up of, well, let's see, what is the acceleration of the plane? Here's our particle. 0. The plane's moving at a constant velocity. So the acceleration of the plane is 0. Now we've got two terms. For our radial acceleration term, it's made up of r double dot minus r theta dot squared. That term must be equal to 0 because the theta-directed acceleration term this way is perpendicular to that one. And so if your overall acceleration of that particle is 0, then each of these orthogonal terms must be 0. So you come down here and you go, okay, that means that r double dot has to equal r theta dot squared, and that is greater than 0, isn't it? Which implies that r double dot is positive. Rely on the mathematics. Feel good? Let's look at the theta term. This theta term is equal to, you got it in your brain yet? R theta double dot plus the Coriolis term, 2r dot theta dot. And this term must equal 0. So therefore, r theta double dot must equal the negative of 2r dot theta dot. What is it we were questioning? We were questioning
just r double dot.
Just r double dot. Well, let's look at this stuff for a second. At A, remember here we are at A. Remember this is at location A. At location A. And you could do this same analysis without just arm waving like we did earlier. You can do the same analysis at B and at C and pin it down using the mathematics. Okay. So right here at A, we knew that r dot was at A, r dot was negative. Theta dot, the angle was increasing. So we can see that this is positive valued. And over on this side, the r was clearly positive valued. And therefore, here's your theta double dot. So your theta double dot is greater than 0 at A. See, you don't have to rely on You don't have to rely on your gut feel for these things. You can rely on the mathematics. Okay, does that take care of it? Like I said, you could go to location B and handle this and do the same thing. Here's the key. That's the key right there, is you realizing that that plane's moving at a constant speed in a straight line. So there's no acceleration existing on it. Okay, good.
Can you explain again why a sub r is, you know that it's 0?
Explain again why a sub r is 0. Okay, if I have two orthogonal terms, and I tell you that the vector is 0, two orthogonal terms, AR and A theta, then don't each of those have to be 0?
Sum of the two is 0?
No, not the sum. Don't they each, they're independent of each other. R is separate from theta. So if the acceleration is 0 and the vector is this, don't each of those component terms have to be identically 0 to give you a null vector? Yeah, to be a null vector. Okay, good. Let's do something with some numbers. Here's one. I'm going to try to cover up my chicken scratch here so I don't take all the fun away from it. Those of you with the book, this is page 75. Here's a pump called a centrifugal pump. And so what typically happens as this pump is spinning, the fluid in the tube here, along this axis, which is coming towards us, the fluid comes in and then it's thrown, the particles of fluid are thrown radially outward. And they follow a certain path given by this hyperbolic cosine function. That's correct. That's the path of the particle if we were sitting there at the origin. And it's given to us in a polar form. The position vector is a function of time. Position as a function of time. And where kappa is given to us as theta dot is the constant angular rate at which the impeller turns. This is called the impeller. Determine an expression for the magnitude of the total acceleration of the particle just prior to it leaving the vane in terms of the inside shaft radius, the outer fin overall radius, and the kappa value, which is the angular speed of the impeller. So it's given to us as R equals R naught cosh kappa T. Kappa is defined as theta dot, which equals, we'll call it omega, which is a constant. That's the impeller's rotational rate. Okay, so I think all we have to do here is start cranking derivatives, and then we're obviously in polar form here. So we'll crank derivatives and see what where this takes us. One other thing before we get started on that, look right over here. If theta dot is equal to omega is some constant, then what do you know right away?
Double dot is 0?
Yeah. Theta double dot is very nicely 0. So we feel good about that. Okay. Now, this is the reason I picked this problem is because it's a little review of hyperbolic functions. Now, hyperbolic functions are really what kind of functions?
Exponential.
They're exponential functions. They're exponential functions. And what this function graphs as a function of time, at t equals 0, let's see if we can remember what Koch's definition is. Here's how I remember them. And you're going to see a lot of hyperbolic functions, particularly if you move into mechanical engineering, for sure in mechanical, vibration theory, things involving radial kinds of behavior, cables, catenary stuff in civil engineering, and so forth. Okay. The way I remember what a Koch function is I know it relates to an exponential. So I'm familiar with e to the x, and so are you. And then if we take that function and symmetrically add it to, and actually we tag a half on that just to help us out a little bit, and then we come up with its symmetric form, the other side here, which is 1/2 of e to the minus x. And then these both have y-intercepts at 1/2. If we add those things together, imagine adding those values together. Lesser and lesser added over to the right as you move out, similarly off to the left. And so what you're going to end up getting is something that passes through 0, 1. You can see it's a pair of functions added together that yield an even function. And what you're going to get is something that's going to move out and asymptotically approach this, because you can see the addition of less and less and less amounts as you move further out. And you can see that symmetrically to both sides. So there's a nice graph of that. And then what does kappa do to that function mathematically?
It might stretch it or shrink it.
It just does a horizontal stretch or squeeze on it is all. And that, in this case, is the angular speed of the impeller. Okay? And then this R0 is simply a vertical stretch or squeeze on the Koch function. So what we have then is a mathematical function from time 0 forward that is going to end up looking something like this, with the y-intercept here at time 0. Koch becomes 1, and you end up with R0 right there. So 0 R0. That's where the particle starts at time 0. And it moves radially outward with the radius growing. Mathematically, the Koch function then is e to the x plus e to the minus x over 2 by definition. So we have this. Well, we're not doing a math class here. What we're doing is applying this to this impeller. So we need to figure out the acceleration of the particle as it leaves the vanes. In other words, when it gets out, there's some point in time here where this r is going to be reaching its capital R value. And then once it's done that, this model breaks down, because the particle then is going to behave, depends on what kind of medium it moves into, it's then going to behave mathematically something different after it gets out off the impeller. So what do we have to do to work up the acceleration? We've got theta dot, we've got theta double dot. Start cranking derivatives here, right? Start cranking derivatives here. So what we need to do then is figure out what R dot is. R naught, what's the derivative of Koch? Sinh. So that we need the derivative of the Koch function of kappa t with respect to kappa t first, and then times the derivative of kappa t with respect to t. Chain rule on it. Be careful there. And the derivative of Koch is sinh, so we end up with R naught sinh of kappa t times the derivative of kappa t with respect to t is kappa. And so we'll move that up forward here. So we have R naught kappa sinh of kappa t for the R dot term. So we have that. Next step, crank out the next derivative. Derivative of sinh is, no, the signs don't change on the hyperbolics. Okay. And if you ever forget this and don't have a lookup table on your hyperbolic functions, you can always go back to the original exponential and crank the derivatives on those things. That takes more work, though. And just for, before we continue on and get the R double dot, just for a quick review, let's look at what sinh is mathematically. It's the addition of this half e to the x with this other one turned upside down. So if I turn this 1/2 e to the minus x upside down, then it's going to lay in like this. And so that graph is going to be your 1/2 of e to the minus x with a negative in front of it. Now imagine you're adding those things together. If you add those together, you're then going to be, as you move off on the right here, you're going to be taking a little bit, because of these negative values, you're going to be taking less and less away from this exponential, and they're going to zero out right here when you add those positive and negative halves together, and you get a graph that looks something like this. Kind of reminds you of a cubic function. Okay? That's an odd function mathematically. And it is the addition of that half e to the x and minus e to the minus x all over 2. So there's your sinh function. And if you by hand take the exponential and crank its derivative, you see you're going to end up with this guy. So you can go either direction on the derivatives, and you're going to come up, there's no sign change like there is in your trig functions, your circular functions. Okay. So let's crank the next derivative here. Kappa is constant, R naught's constant, so all we have is the derivative of the sinh here. So to make this a little quicker, let's just do it. So we're going to end up with a R naught kappa squared, aren't we? Cosh of kappa t. R naught kappa squared, cosh of kappa t for the R double dot. And the question asked, determine the expression for the magnitude of the total acceleration of the particle. So we need each component, don't we? We need the radial component of acceleration, which is R double dot minus R theta dot squared. We need that one, and then we'll have to get the theta one worked up. So the R double dot, we have our R naught kappa squared, cosh kappa t. Take away from it the original R times our kappa squared, right? Original R here times our kappa squared. So we're going to have R naught minus R naught kappa squared cosh of t. Kappa t. And those zero out, don't they? Which means, Ian had it, if the AR is 0, then that means
It's just moving constantly away from the origin.
oh, well, hold it. Hold on. Let me go back and pause for a second on that. I thought you had that right, and I'm not sure. Okay. If it's moving constantly away from the origin, that means its R dot would be constant. which means that its r double dot would be,
Oh, we needed the constant acceleration.
yeah, see, there's two things.
Right.
See, those two terms. There's that r double dot guy going out minus the r theta dot coming the other way, and it's the net sum of those two is 0,
Right.
which we actually see right here. So these guys happen to remain equal to one another in value. Okay, so that's kind of interesting.
It still it may not translate though to moving constantly away from the origin.
Right. It doesn't translate into saying that it's moving constantly away from the origin.
Or because of the theta acceleration, it's just.
Yeah, because there's a theta.
I don't think I meant
There's
it.
a rotational velocity going on there
I mean,
too.
if you ignored though the movement left and right, imagining on an arc around the origin, then it wouldn't be the arc itself is moving at a constant rate away from the origin.
I'll talk to you about that later. Okay.
All right.
Not sure. Okay.
So
Okay.
that, that means that when it passes on not on a drawing, it has to have some velocity, and so that we should be looking for some v naught term to pop up somewhere if we wanted to know what the particle is actually going to do. We'd have to know the velocity the velocity at which it passed on not,
The velocity at which it passes where?
or not.
Well, actually, it comes in there with. Well, we could figure that out, but I think it comes in with a 0 velocity initially, because what it's doing here's your impeller turning, and there's a tube here with the liquid in it, and the liquid's coming in and then being thrown out radially. So it's coming in here, and as it turns and then starts to move outward radially because of the impeller fins, that right when it first enters there, it's got 0 velocity.
So if it has 0 velocity when it comes in, and its radial acceleration is 0, how does it move away from the origin?
Well, that's a good question.